So look here at some of the uses beyond what we've been doing with binomial and geometric distributions. This is actually going to build into what we're going to get into after this particular lesson. So the first thing, just a quick reminder, or this isn't necessarily a reminder, but it's something that's not in your packet, but you're going to see if you look on the formula sheet for the AP stat test, you see this formula, probability x equals some number k. And what it is, it's the binomial formula. And it looks kind of strange and foreign. But I'm going to take a moment and point this out to you. We've actually been kind of doing this. It looks kind of big and scary, but just on the off chance that maybe you see it within a multiple choice type question, let's say, the 6 monkey scooters, and then I think the probability of a defective was, 40%. And the question might be like, how likely is it that we get, 4 defective scooters? All right. How likely is that? Well, the binomial formula, basically, we've been using it already. So, for example, the P to the K, right? Well, these two pieces you're pretty familiar with. You're basically just saying, all right, well, there's 4 defective scooters, so we have 4.4s, and this 1 minus P, well, that's the probability it's working, and 2 of those. All right, if you think back, when we did this the long way, we'd say, all right, we'd have to have defective, 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 working, right? So there's your 0.4 to the 4th, and your 0.6 squared. But we're also aware that, hey, there's a lot of ways we can combine these 4 D's and these 2 W's. And we used NCR, right? So we used that NCR function. Well, that's all this N over K is. So what that is, N is the total number. So 6, choose 4. All this is the NCR. But that's just the way that it's written on the formula sheet. So sometimes you might see, I've seen this happen on the AP test, and it might say, instead of actually giving you the actual probabilities, they'll write it in binomial formula. So you just want to be aware of it, right? So that would be like choice A, and then choice B would be, 4 out of 6, and then maybe they kind of move stuff around. So you just have to know what goes where, and then see, maybe it's 2 out of 6. 0.4 times 0.6. So they just kind of move stuff around, and what we'd have to recognize is how to appropriately use that formula. So it's what we've been doing is just a slightly different look at it. So here's what we're after today. We start thinking about, so suppose 10% of lottery tickets are winners. So if you buy 20 tickets, how many would you expect to be winners? Right, all of a sudden, here's this term, we've seen this before. How many tickets would you expect to buy before you get a winning ticket? So all of a sudden, we're going to take a look here in this particular lesson on expected values. Remember, expected values, that's just another name for the mean. So if it's a binomial setting, you guys probably already have a good idea here. Lottery tickets, right? Either win or you lose, so there's 2 outcomes. We have a set number of trials here, 20 tickets. Each ticket's independent, and the probability of winning is always 10%. So this is binomial right here. You probably already have a sense for exactly how to do this. If we bought 20 tickets, if 10% of them are winners, you'd probably expect to get about 2 winning tickets, right? That's because that's 10%, 20 is 2. So you've already got a sense. The expected value, right, we just said, is another name for that is mu. So there's your expected value. Just N times P. So for the last example, that was 20 tickets times the probability of 1 equals 2. Standard deviation is a little bit different, right? Before, when we did something like standard deviation, we would have had to do the whole big chart, X, probability of X. And if we're buying, 20 tickets, if it's number of winners, we'd have to go all the way to 20. That'd be a really, really big chart. But, then we put all of our probabilities in here, and then we'd have list 1, list 2, and then we'd do 1 bar stats, right? We would have done 1 bar stats, L1, L2. And that would have given us our mean and our standard deviation. However, Since it's binomial, there actually is a formula for it, and it's the square root of NPQ. And Q is just 1 minus P. So for us, in that previous example, then 20 tickets, probability of winning is 10%, the probability of losing is 90%. If we go back to our DVD players, so I think there were 8 homes that we were visiting yesterday. So the expected number of homes of the DVD player, remember the probability it had a DVD was 90%. So the expected value would just be 8 times 0.9. So we'd expect 7.2 homes. Again, it's okay to have decimal. So I'm going 8 times 0.9 times 0.1. When I come back and take the square root of that, that is 0.849. So there's your mean and your standard deviation. So in other words, 68% of the groups of 8 houses will have between basically 6.2 and 8.2 DVD players. You wanted to go back to your empirical rule. The winning caps, right? So we got a 12 pack, so n equals 12. Remember the probability of winning is 1/6. So the expected number would be n times p. So we expect about 2 winning caps. And then the standard deviation is the square root of 12 times 1/6 times 5/6. So that's going to be approximately 1.29. So 68% of 12 packs will have between 1 and 3 winning caps. 95% will be between basically 0 and 4 winning caps. If we go up and down about 1 standard deviation using our empirical rule. The other thing, I can go all the way back. If we're going until we win a ticket, so in 20 tickets, we got a definite set number in the first part, but down here, how many tickets would you buy before you get a winning ticket? There's no set number, so here's the geometric. Man, it's 10%. Most of you probably already have a sense. Well, that's about 1 out of every 10 tickets, so you'd expect to buy 10 tickets before you get a winner. So the formulas here, right? The expected value or mu, right? So for us, 1 over, if it was 10% of winners, 1 divided by, well, that was 10. Standard deviation is a little bit different. So Q, again, that's 1 minus P. So for us, that would have been 0.9 over 0.1 squared, and then we take the square root of that. And that is 9.49. The average number of villagers that would take until we meet an actual Hawaiian. So here we don't actually need n, we just need a probability. So it'd be 1 over 0.8. So 1 divided by 0.8. We'd expect to meet 1.25 villagers. If we want to do the standard deviation of this, so we'd do Q 0.2 over 0.8 squared. Take the square root of that. So one way to look at this one, so 68% of the time, we'd meet our first villager, go up and down half between basically the 0.75 and 1.75 person. So in other words, somewhere between 1 and 2, we'd meet our first Hawaiian.